Hi Nikhil, hi Santosh.
Hi, Praveen.
Okay, Santosh, I can hear you. Wait a second. Both of you can hear me?
Hi, Praveen.
Hi. Okay, so yes, we missed a lot of class. So we will try to cover. Actually, missed two classes, not a lot of classes. So we will try to cover at least two classes in this week plus normal weekend classes we'll do. Okay. So today is Monday. We are covering one class. We'll do one more class sometime, and then we'll come back to our regular schedule of weekend two weekend classes. Okay.
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 Yeah. Okay. Let me ping Sukanya. Was there any assignment?
Yes.
Yes, Praveen.
Okay. Have you sent assignments?
Yes, I
Out of the two, I sent one, Praveen. The second one, I was a little confused.
Okay. Okay. So let me download first assignment. Kth node from end. This is one code. There is some submission by linked list implementation. So you can see the code, both of you.
Yes, Praveen.
Okay. Okay, then let's discuss this code, and then we start tree whatever we stop with, and we'll wait for Sukanya for her to join.
Okay.
Yes, so this is the linked list implementation using simple node, and then we have maintained a head, we have maintained a tail, and we have also maintained a circle size equal to 0. Okay, we have insert method, which what it does, and then loop node is what is where the loop node. Okay, so we have this first method insert add head, which is nothing but simply creating a new node with the value which we want to insert, and then new node dot set next equal to this head. Okay, so we are pointing our new next of the new node to head, and then changing our head equal to new node. Simple. This is simple insertion in a linked list add head. Now he has also implemented insert at the end, which is not a very default thing, but we can always implement whatever we want, and it's good to implement it. So an easy way was to maintain a tail. Otherwise, we would have to traverse all the way from head till tail and then insert, which would be order of log n, where n is the number of nodes in the linked list. But it's better to maintain a tail so that we can insert easily. Similarly, here what we're doing is we are creating a new node with the element, and then we are what is head equal to checking something head equal to we'll check this edge condition later. Simply doing is tail dot next is equal to new node and tail equal to node. Simple implementation, very simple. Nikhil, you can get this simply.
Yes, Praveen.
So tail dot next is equal to the new node which we just created. If there is no node, if no node exists, in that case you handle that thing as well. Node dot set. So if head is null, then set node dot set next equal to head. Okay, and head equal to node, tail equal to node, which is also correct. We have to handle both the cases. Now you people are improving. You're trying to handle all the cases, which is good. Okay. So do we have to do any check over here?
Sorry,
Nikhil,
Praveen.
Santosh, do we have to do any edge case check here, or do we have to
Yes,
handle
I
what
haven't.
if?
I haven't maintained the tail in that insert head.
Yeah, so we have to maintain if we have to change our tail as well. In case there is no node, there is nothing in the linked list that is head is equal to null. In that case, we have to set head, which is correct, plus we have to set a tail as well. So if head, then it's okay. To create new node, then new node set next is also okay. If head is already there, then we'll do this head equal to if head is not there, and then just a second. Else. So if head is not there, in that case, tail is equal to new node, and head is also equal to new node. But if head is there, then don't change the tail. This is correct. Which is just to make it simpler. Not of head. Okay. Good. This look good. Okay. Now this is insert. One more insert, and this is insert at some position. Okay. So let's try to go through this code as well. Current node is equal to head. Okay. So, and then we are doing it, position is equal to 0, length is equal to position is equal to y. If position is equal to 0, then insert head. Okay. I mean, we don't have to handle it separately. We could have handled simple loop only, but okay. So for length is less than position minus 1. Okay. Current node dot next is not equal to null. Length plus plus. Current node is equal to current node next. The moment you find, okay. So the moment either you reach the end of the loop, which is length is equal to position, or your current node dot next equal to the either you reach the position or you just reach the end of, like you reach the L null. In both the cases, you come out of this loop, and then if length is equal to position minus 1, then insert. Otherwise, position is greater than linked list. That is also correct. So this is loop is correct. Now what we're just doing, just let me see here what we're doing is, if length is equal to position minus 1, in that case you also, so there are lots of if else which is not needed. I mean, this is correct.
Okay.
But if I write, or someone who has like cerebral experience, what if they write, what will happen is we can write in least number of if else. Otherwise, this is correct. This is going to work. So I'll write a code later. I'll write and give you code, which is much more. It won't have a lot of if else. That's it. Nothing else. Otherwise, that will do the same thing as well. Okay. 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 This insert is also correct. This is print linked list. I don't know. Oh, there's a get kth node. This is kth node from last or kth node?
Kth node from last.
Okay. Okay. So even Nikhil has submitted the same thing. Let me see what you have done. But current position is less than position. Okay. Then you do just P1 count plus plus. The moment you exceeds, and that moment P1 is not equal to, by P1 is not equal to. Then you now from here you start both P1 and P2 as well. So
yeah,
the moment you reach P1 will reach end first. At that point, the moment P1 reaches, that is the point where your P2 will be at kth position. So what you do is this is correct. So this is correct. I hope Nikhil would have implemented the same thing. This is now reverse linked list. One more linked list.
Oh yes, Praveen. I did the same thing.
Okay, we'll see your code.
I think I sent you the other program. Let me send you that one. One sec.
This one.
I think I sent you the first implementation.
Okay. This is care node from linked list. This is one solution you have also given. Let me find kth node. This is your find kth node. No, this is kth node from start, I guess.
Oh yes. I one second.
Kth node from last. Yes, Nikhil, do you have your code or shall I go ahead now?
Yeah, Praveen, I just sent it to you.
Okay, we'll look at it later and we'll leave it down. So let me just go through the reverse linked list code, which is again submitted by Santosh only. So this is reverse linked list, and current node is equal to head, reverse equal to null, next, and you have, let's say, all these three, and you're just going through this completely one by one and changing the point. Next is equal to current dot next, current dot set equal to previous, previous equal to current node equal to next. Okay, this is correct. Reverse linked list, reverse linked list. Now that you have solved, both of you must have solved reverse linked list. Nikhil, you must have also solved linked list. If not, you do it again.
Yes, I had already sent a previous class.
Okay, nice. The new question for your reverse only is a little bit tricky, a little bit changed now. The word, how to change it? Assignment. I'm writing assignment.
Praveen, we can write on that Google document.
Okay.
So that we can directly.
Don't worry. I will also. It's easy to write here. I'll paste there. I'll paste there everything, whatever I write here. Okay.
Okay.
Yeah. So reverse a linked list in group of k. Did we discuss this question? No.
No.
Okay. So what this means is, suppose this is a linked list. And I tell you to reverse this linked list in groups of 3. How will this look like after reversing this? Does this look like 3,
2, 1, 6, 5, 4, like that.
9, 8, 7. Okay. You get the question?
Yes.
Okay then. This is your again assignment. You'll do it when the class is over. And this is how it should look like. In case, suppose the input was or k equal to 4, how it look like? Let's do when k equal to 4. It will look like 4, 3, 2, 1, 8, 7, 6, 5, and then 9. Okay. Okay. Moving ahead. So I don't know where is Suganya. She has to join. We said that we'll talk about trees in detail in the last class. We just started with something.
Praveen, I did not get one of that, meaning this finding circle one.
Okay. Then let's discuss that as well. So I think Santosh has tried to write that code as well.
Yes.
Yeah. So initial question was, so did we talk about find the circle, size of circle, starting point of circle, all these things? Did you talk about all 3 or only one of them?
Yes, I had submitted for that code as well.
Okay.
That was
let's talk about the first part. This code Boolean is circle is just checking if the linked list is a circle or not. Simple. Or is it checking both? It contains circle or not? Santosh?
It's checking circle as well and printing the size of the circle.
Okay, both things doing. Okay, let's go through this code first. So is circle, actually this code, if I'm not wrong, this code is contains circle, not is circle. The is circle is slightly different from contains circle. Okay, so is circle is just like am I part of the loop or not? But like am I means head is part of the loop or not? That's simple difference. is circle compared to contain circle. Like this head is not part of circle, but there is somewhere ahead in the linked list where there is a circle. Okay, but no problem. We'll go through this as I'll change the name of the method here. So this is contain circle only. Okay.
Okay.
So what we are doing here is first we have one pointer p1 and which is head, and one pointer at p2 which is head dot next. Now while p1 next is not equal to null and p2 is not equal to null, and p2 is next also not equal to null, just increase p1 and p2, both of them. One of them will increase by just move ahead by one step, dot next, and other will move ahead with dot next. Okay, so this is fast pointer, this is slow. This is slow pointer. This is fast pointer moving with 2 speed. Now, if while doing this, either of them either reaches the end of the linked list. Nikhil, you are following me? So this is what we are proving by. Yes.
Yeah, Praveen, what is the meaning, intuition behind taking the other fast pointer is 2 times?
No, there is no, sir, there is, but it's not about why 2 pointer faster, not 3, because, whatever speed you take, they will meet at some point, for sure. Because one is moving with speed of 1, another is moving with speed of k, they will meet. But what is the best option for us? So the best option should be moving with the speed of 2. Otherwise, what will happen? Suppose if you take if you move the second faster pointer with a speed of 3 or 4 or 5, in that case, when both of them comes into the loop, meeting for them to meet, it will take more time. So it's like jumping 4 each. Suppose k equal to 4. Suppose the fast pointer is jumping by 4 position. In that case, there are chances that they both will keep on rotating in the circle, but they will not meet. And we want them to meet. That's why we are making sure that they meet also, and as soon as possible. That's a simple intuition behind why only with a speed of 2 and not anything greater than 2. So again, compared to real life, it's like if you move slower, yes, the chances that you will meet slow, but you will meet within one loop only. In compared to if you jump by 4 or 5 or 3, then you might meet faster. You might meet in a single loop, or you might take 2, 3, 4 number of loops. So that's the reason we have taken one moving the speed of 1 pointer every time, and another moving the speed of more than 1 pointer, like 2 pointers at a time.
Okay.
Can someone give a meeting ID?
Okay.
Okay, find the meeting ID. Got it. So Nikhil, do you understand why are we doing 1 pointer with a speed of 1 and 2, second with a speed of 2? Again, I'll repeat. If the faster pointer is being moved with a speed of more than 2, then the chances of them meeting in single loop or second loop will be less. They will meet for sure, we know, but they will meet in more than one loop. It will take more than one loop for them to meet. It will take more than 2 loops for them to meet. That's the only reason we're making the second pointer moving slower. Okay.
Okay.
Okay. Now. Now we are here, either one of them reaches the end, either P1 or P2, one of them reaches the null position, or they meet somewhere. This is like breaking condition. If they reach end, then just tell key there is no circle. You have not handled that. Yes, you have handled. Okay. So if they meet somewhere, if P1 equal to P2, we just make a circle equal to true. And after that, we loop node is equal to P2, and then we just rotate P1 again in a complete circle because they have met somewhere. Because they have met somewhere, is P1 equal to P2, then it means this circle is true, which is correct. And then we start one more loop internally. This one more loop which starts from the meeting point, and then we keep on moving. But I don't think we need to. Santosh, instead of just checking while P1 not equal to null, we simply have to check while P1 equal to P2 not equal to P2, because there won't be any null anymore because they're part of the loop.
Okay, correct.
Simply check while P1 not equal to P2, keep on doing this, and circle size increases. And after that, we have
Praveen, is there any way without fast and slow pointer to find out if it contains a circle or not?
Is there any other way than this? Let me think. I do not think, like, I can't think of any other solution right now, but I'm not sure. So,
Okay.
right? Like, do you have something in mind?
No, I was just thinking about it. I also can't think of anything.
Okay.
I mean, like, yeah.
So I don't think we are starting from the head, which might not be part of the loop, and we have to decide whether this contains a loop or not. There is no other way other than 2 pointers. Single pointer cannot, with just single pointer and without making any change to our node structure. Other solution could have been change the structure of the node, which is like make one more instance variable called visited, and then whenever you go to that node, just mark that as visited. That solution can also work, but that will only work if we are allowed to change the node, that we are allowed to store a visited thing. Otherwise, we'll have to have 2 pointer. We just can't solve with 1 pointer. Okay.
Okay.
Okay. So now we have found our loop. The moment we find our loop, we have also found the size of the loop, circle size. We have our circle size as well as we know this contains circle. Otherwise, this could have just written no circle. Okay. Now, next part is get the circle starting point. So, how can you explain, Santosh, what are you trying to do here? How to find the starting point of the circle?
Yes.
Okay.
Oh, I'm taking 2 pointers over there. One is the loop pointer where we both the already P1 and P2 pointers made.
Okay.
I'm taking one pointer name as loop, and one more pointer I'm moving ahead from the head onwards.
Okay.
So I will complete the one circle from the loop. So if I didn't met the starting pointer, then I will increase the starting pointer to next node. So yeah. So the loop pointer I will keep on.
This point, do you have one pointer at head, one pointer 2, yes, and one pointer where they met, pointer 1. These are two things. After that,
so I will keep on repeating this loop pointer. If I didn't met there, then I will increase the loop pointer to next node. ptr1 dot get next. And
I do not get this. Let me draw something for you first. So what we want to do is, there are 3 cases. One is you have a straight part and very small loop part. The other case is you have very small straight part and very big loop part. And we have a third case, a decent straight part and decent circular part. So just keeping these 3 in mind, we have to find this position. We have to find this position. We have to find this position. Anything is any kind of input is possible, and we just solved till now. Okay, we had 2 pointers moving from starting. One was moving faster, one was moving slower. They both met at some. Is there a color change possible? Leave it. So suppose both of them met here or here, or somewhere here. Okay, we have done till now. So our solution, which we have done till now, is we have found, yes, it contains a loop, and second solution we have found a size. In both in the case what we assumed is pointer P1 and P2 that met here or met here or met here. Okay, we have done till now. Now what we will do, Santosh, can you explain me What do you want to do? You are keeping one pointer at the head and one pointer here. What you're trying to do? Let's call this as head, and let's call this as meeting point. Okay. What do you want to do now?
So the meeting point, I will rotate this continuously rotating this meeting point node, correct?
Okay. So this part of the code.
Yes.
Okay. So this is pointer one dot is starting at the loop. You're increasing that one by one, and pointer one is not equal to. You want to rotate this completely one circle, and then while doing this, if you do not meet your pointer,
if it is meeting with the it doesn't meet with the head pointer, then I will increase the meeting pointer to next one.
Okay, got it. So okay, so what will the time complexity of? I got your point. So other people, Nikhil, Sukanya, are you with us? Like, what are we doing? This is a question I gave in previous classes. Find the first, tell whether this linked list contains a circle or not. If it contains, what is the size of the circle? And after that, tell me the starting point of circle. Sukanya, did you know this question earlier?
No, I didn't know the question. I saw the solution in the email thread, so I thought it might be some finding a loop in the linked list.
Okay. Anyways, so his solution currently is, after we have found the circle and the size of the circle, we now third part is get the starting point. We have to find this point.
Yeah.
So what he's trying to do, what Santosh has tried to do is, he is just moving one step ahead in the linked list, and then checking if that pointer reach the starting point circle or not. And how he's doing that? He's just rotating this another pointer which was here completely in the circle, one full round. So agar head equal to head dot next kiya, to yahan pe aayega, and this will take one full loop, and they won't match. Next again, he will just move it one step, and this will again take one full loop. This will again not match. Again it will go one step, and this also go one step. This again won't match. So when will this match? At the point when this head, which started from the head, when it reaches here, at that point of time, this second loop will take full circle, and then it will say, yeah, I have matched now. So is that what you're doing, Santosh? Correct?
Yes.
Praveen, like, how are we initializing the pointer in the loop?
Initializing the pointer, you mean which line? Can you say which line? Line number 137, which line are you talking about?
Oh, okay.
Nikhil, anything?
No, that's it.
Okay. So actually, this get circle starting point, he has already he started from one head, and another node he's talked about is loop. This is the point of meeting actually. Okay. This loop which is initialized is like, this is the point where they met in the first point only when we were finding the circle. So using these two starting points, using this head and the meeting point, he is trying to find if where is the starting point of the circle. Let me call it loop instead of just loop. Let's call it meeting point, the first meeting point. Okay, this is the point where they met first. So using these two, we can find the starting point. What we want to find is the starting point of the circle. And what he has done is correct. That's the brute force approach. We will just move it one step and check whether that is the starting or not. How do we check that? We just take a complete loop. Now, what is the time complexity of this solution, by the way? Nikhil, Santosh, what is the time complexity of this solution of finding the starting point?
Order of n, I think.
N, where n is?
Number of elements in the list. Number of nodes.
Number of nodes in the linked list, loop, whatever. Okay. Yes. Nikhil, what is the time complexity? Can you say? What will the time complexity be?
Not sure. One sec. Let me.
So before we go through the code, let me repeat the solution. Okay, pseudocode or just solution. What he's trying to do is, for every node, he's trying to go and check whether that contains the loop or not. So he just jumps and then takes one full circle. Then he jumps once again. Takes one full circle. Then again jumps one, takes full circle. So he's doing for all the nodes.
N square everything.
N square?
Yeah, because he's doing it for all the nodes, and every node is taking that circle thing.
Sukanya, you there?
Yes, I'm there.
So time complexity, can you say what is time complexity?
I'm not understanding the loop, so how will
Okay. Okay. So let's not go through the loop then again. So Santosh, suppose take a generic average case where the size of the linked list is n, and n by 2 is a straight part, n by 2 is a circle. Can you think now what will the time complexity be? N by 2 is the size of the straight part, and n by 2 is the size of the loop. What will time complexity? You can think again.
Then it should be n.
N. No, so what he's trying to do, what Santosh is trying to do is, for every node in the straight linked list, for every node in the straight part, he's rotating completely into a circle. So it is like n by 2 plus n by 2 plus n by 2 plus n by 2, which is total is n by 2 into n by 2, which is n square by 4, which is n square and not n. For every loop in this part, he's jumping one node. So this is what he's doing now. Pointer equal to pointer dot get nice. He's okay. And for every pointer 2, he's checking full loop. There's one more loop here, full loop. Okay, so there's one loop over here, which is going for all the nodes in the linked list. Pointer 2 equal to pointer 2 to next. And for every of that, he's doing one more loop here, full loop in the complete circle. Okay, the complete circle he's rotating, and this rotation is n by 2 times. And so this loop is n by 2. This part is n by 2, and this same n by 2 he's doing n by 2 times, like length of linked list times. And in average case, it would be n by 2. Suppose n by 2 is the straight part, and n by 2 is the size of the loop. In that case, it will be n square by 4, and hence n square. Santosh, do you get this? How it is n square and not n?
Yes, I get.
Okay. Okay then. So, but still, this is not good enough. We want to do it a little better than n square or whatever. Like we want to do it order n only. Can we do it order n only? Like finding the starting point of circle, and what do we know is we just know that this is the point of meeting. I mean, this contains a loop for sure, and this is the head, and this is the point of meeting. These are only two things we know. This is the point of meeting, and this is the head. Using these two knowledge, we have to find the starting point, but in less than n square, or let's simply say we want it in order n. Can we do in order n? So prior to this, what we talked about is how we are finding the circle is we are moving one of them with a speed of 1 and another with a speed of 2. So wherever they meet, this point of intersection, this point of meeting, there is something special about this. So forget about this case. Now just tell me, suppose there is a circle. Okay, there is a circle of size C. Okay, circle of size C. Okay, and now suppose both of them start from the same point. Both of them start from the same point. One moves the speed of pointer, slow pointer moves with a speed of 1, and fast pointer moves with a speed of 2. Where will they meet again? Like they both start from the same point. Where will they meet again? Suppose this is a circle. They both started from here, and one was jumping only one step at a time. And the other is jumping 2 steps at a time. Okay. So when will they meet again? At what point?
The same point where they started.
Same point where they started, correct? Both of you? Other two? Nikhil, Santosh, is this correct? They will meet again here only, same point where they started?
Yes, I think.
Okay. Why do you think? I'm not sure. So what is the thing? Let's think. It's like your, and not just
the fastest pointer completes the entire circle, and the slower pointer would be at the half of the circle, correct?
Yeah, I agree. Yeah, I think that is the
Yes,
thing.
Yeah, faster
it
one
will.
complete one full circle, we will just be at half only. Then it completes one
Yes,
more circle, or it will meet here. Yes.
yes.
Okay. Okay. So we agree with this. If we move with one speed one, other with speed two, they both meet, but at the same point. Now what if the slower one starts from here, but the faster one starts from a little bit ahead, like from here? Where will they meet again? So the slower pointer was here, and the faster started with some after a step k only. Like it had a lead. It took a lead of k, and then both of them started at this point. Where will they meet again? Slower started from 0 and faster started from k. Where will they meet?
I think not in the both the places. Some different place, some different node they made.
Tell me where will they meet? If we can think. Or let me make it opposite. What if slower has a lead? S is k step ahead, and fast is starting. Where will they meet now? Where will they meet now?
At slowest, meaning where slower?
Yeah, slower pointer has a lead of k. Slower pointer starting, both of them start when they start. Slower one is k step ahead of faster pointer. Where will they meet again? Do you think they will
Opposite
meet?
to slower pointer.
Do you think they will meet here, which is
Yes,
k? Agree? They'll meet here.
yes.
Okay. So what we have figured out that if slower has a lead of k, then they meet at k before faster. Is that correct?
Mm-hmm.
So now just assume the same thing happening. With this knowledge, what we are doing is when our slower pointer reach the circle at that point of time, when our slower pointer reach the circle at that point of time, faster pointer would be somewhere here. Assume, okay. When the slower pointer reached the starting of a circle, our faster pointer would be somewhere here, which means which we can say is slower pointer had a lead of this size, of this much, or we can say either we can say anything. Either faster point had a lead of this much, or we can say slower pointer had a lead of this much. Can we say that?
Praveen, can you repeat that? Like, or you just...
Okay. Yes. So we know from this example that if slower pointer has a lead of k, then they will meet at a point k before where f started, where faster started. Okay. This is we know from our knowledge. Using this knowledge, we are trying to say that when I was moving my slower pointer with a speed of 1, 1, 1 and faster pointer with a speed of 2, 2 and 2, at the point of time when slower entered the circle, at the that point of time, faster pointer was somewhere here. Okay, I don't know where, but it was somewhere here. Is that okay till now?
yes, yes.
Okay. Now what I can say, at the starting point, F was here and S was here. So either F had a lead of S or we can just straight reverse in reverse way. S had a lead of this much. Okay. Now both of them are starting in a circle. Now both of them are starting in a circle this much, with S having a lead of this much, which is suppose if this is K and this is, let's talk about this is K2 only. So anything. Suppose this is K2. Okay. I'm just saying it's slower when it just entered a circle. It had a lead of K2. Now they met somewhere here. Now this somewhere here should be what? This somewhere here this should be equal to, okay, now I have given you enough hint. You have to use this much of hint and prove. So what you have to prove is, actually I'll give you a solution now. Before I give you this proof, how I'll give a solution to how to get circle starting point. Okay, this is a question which Santosh has solved in order of n square. I'm giving an order n solution. What you have to do is prove that this is correct. Okay, otherwise I'll do the proof in next class. But what you have to prove is, given them met at this point. Now if I start a pointer from here head and another pointer from here meeting point, I'll just keep them both. I move both of them with a speed of 1. Wherever they meet first is the starting point of circle. My one pointer P1 started from here, and another pointer P2 which started from here. What I'm saying, the way to find the starting point of the circle is just move P1 with a step of 1, 1, 1, 1, and P2 with a step of 1, 1, 1, 1, and the first meeting point will be the starting point of the circle. That is what is, and this is correct. This is order n, and this is correct. Do you understand what solution I'm giving is? If you move P1 from head and P2 from the meeting point wherever they met, and you keep on moving them with one step, the meeting point, the first time they meet, is the starting point of the circle. Correct?
Yeah.
You get a solution, and you have to prove this. Yes, this length. You have to prove that this length and this length, this straight part of the linked list, is either equal or something that they will meet here only. You have to prove this. I have given you a solution. Think over it, and we'll do the proof in next class. Okay? And this solution is order of n. This solution is order of n, not n square. So let me
write. The length of the node is not equal then?
What is not equal? This is not equal to this, you're saying?
Yes.
Yes. The thing is that's what the proof you have to do is, either this will be equal to this, or just a second. Yeah. So either this from P to yes. So either this length will be equal to this length for sure, or it can be that this full length plus this is kind of n into k plus k. What I'm saying is this bigger straight part is n into size of circle plus this extra part plus equal to this. I mean, this length L will be some in the form of n into c, some lambda times of this size plus k, if not equal to. So this straight part, let me write a little bit more. So you have to prove, given all the things I told you, you have to prove that length of the straight part will be n into circle plus k. This is where n is any random integer and c is the size of a circle, which we just derived. So length of the straight part will be equal to this, and k is this part where point of meeting till the start of this k. So we know we have to prove this. Actually, we have to prove this. Simply, we have to prove this. And with this proof, if we prove this, then my solution will work every time. What is my solution? My simple solution is we have our head equal to something, and we have our meeting point equal. Okay, we have these two things, and my solution says while head equal to not equal to meeting, just do head equal to head dot next, and meeting point is equal to meeting dot next, and they will meet for sure. The moment they meet, that is return that point. This is my solution, which is order of n. We only have to prove this, and this proof will only be this solution will only work only if we prove the where is the equation I gave. Yeah, this solution will work. Okay, guys, do you get this solution? By the way, what I'm doing here?
Yes, Praveen.
Okay, so this thing can be proved. Yes, this is correct. If they meet, that is a point of starting point circle. To prove that is correct, we have to prove this line. If we prove this line, that solution will work. The length of the straight part of the linked list is L, which is equal to n times into C plus K, where L is the straight part of the linked list, C is the circle of size of circle, and K is this point, this length, the length where they met till the starting point. Given these three things, we can prove it.
What is n, Praveen?
Yes.
What is n?
N is any integer.
Okay.
Lambda. Okay, that kind of thing. So in case when this is very long, straight part is very long, this n will be high. Okay, 5 times of loop plus k. In case this is very small, it will be 0 c plus k. Okay, they're equal. N can be any integer. Okay. Okay. If you try to prove this, good. Otherwise, we'll do in next class. I'll move ahead. Okay. So we'll do trees today. Sukanya, did you go through the lecture video in my previous lecture video?
It was not uploaded probably.
Seriously.
Yeah, Praveen, I don't think we didn't. I just checked the channel.
Okay, then I would have missed something. Okay, then I'll upload both the videos today only. Okay, I don't know how I missed. Okay, I'll upload today both of them. Let's start with the trees now. So in the previous class we discussed. Can you just a second? Can you see the doc?
Yes. Binary trees.
Yeah, nice. So in the previous class, we'll talk about trees and what is special about these trees now. So we talked till now we have just read about all the linear data structure. What do you mean by linear data structure? That all the elements are placed next to each other one by one, and we can reach only one. When we iterate, we just move to one next element. We do not choose whether to go in the first subpart, second subpart, left subpart, right subpart. Those kind of we have not done till now. All the structures are linear. But
Praveen, did you upload it as a double linked list, circular linked list?
Yes, we covered that thing as well. Double linked
list. The session is uploaded. Session 5 probably.
Yes. Yeah.
Right.
So
got it.
We just discussed a little bit about tree and not completely. We just discussed a little bit about the tree. We'll repeat the same thing and then we go ahead. So binary again now. So that's why we'll read about a non-linear data structure like trees, like heap, like graphs, and other things. These are the non-linear data structure we'll read about. And what about the linear structures like array, linked list, stack, queues? These are linear data structure. Okay. So what is this? benefit of reading these non-linear data structures, these structures help us maintain some hierarchy kind of thing, and they also provide moderate access and get and insert, delete, fetch. Those operations become much more improved, especially if you simply talk about it, it reduces from linear to logarithmic. Most of the operations reduces from our linear time, which is order n, to our logarithmic time, order log n. This is the benefit they provide. If you store the elements in some order, if you store randomly, it might not have that benefit every time. Insertion might have that benefit. Deletion also, but deletion and finding might not have that benefit. But if we store in like non-linear structure as well as with some order, then our insertion, deletion, everything becomes very fast, like becomes logarithmic compared to linear if it was linear earlier. Okay, so that's a benefit we get from non-linear data. And the first one we are reading about is tree. Then we'll also cover heaps. Again, these both of them are like tree-like structure only. That the difference is something that's slight different, but both of them are tree-like structure. We have left, we have right, and then we have children. That kind of structure our heap also has. So among trees also we can have any children of node, but we do concentrate a lot on binary tree only, and not on ternary tree or n-ary tree. We just concentrate a lot on the binary tree. We read about binary tree a lot, where we have left children, we have right children. But a tree can have any number of children. If you see this structure tree, where J is the root and it has two children, F and K, and then F has two children, AH, K has one children, Z. So this is a binary tree. What is a binary tree? A tree where every node has at max two children, left children and right children, left child, right child. Okay, that is what binary tree is. But not necessarily all trees are binary. There are trees where they have n children. How do we store that? If we see the implementation a little bit, if we go and let's try to see the implementation of a tree. So how does the node of a tree look like? It has some key, it has some value inside it, data inside it, and it has a left pointer left and right pointer right. Okay, we have 2 pointers. That's how the simple implementation of linked list tree is. It's like quite similar. It's quite similar to our double linked list as well, where we had data. It has previous node and the next node. In terms of that structure, it is similar. Just that what we store and how do we perceive what left means, what right means. But overall, they are equal things. Similar implementation. We have left pointer, we have right pointer. Now using this node, we have our B tree implemented, where we just have a root. That's it. We just need the root of the tree. That is good enough to access full tree. We just maintain the root, which is of this node type, and we have our tree here. This is a simple, very simple implementation of a tree, where we just maintain the root node. That's it. So this is a B tree implementation. But what if we want to implement our binary tree? Instead of binary tree, if we implement ternary tree or four children tree or n-ary tree. So what we can do is simple changes. We don't know how many children can have. It can have any children. We just implement an array of child. That's it. Okay, this is the change if it is n children. Otherwise, if we had only 2 children, we can just maintain left and right child. Okay, people, that's simple implementation of a tree. Okay, I'll move ahead now. So we'll talk about binary tree only first. We talked about these things, I don't remember, but if you have got this, what is a binary tree, then just answer me some questions. So which is like properties. If you understand these properties, it will help you in thinking. It will help you a lot in thinking the time complexity of all the problems we'll solve using tree. So can anyone tell me, the question is, what is the maximum and minimum height of a subtree of a binary tree given there are n nodes? Let me write the question again. So question is, what is the max and minimum possible height of a binary tree with n nodes? Everyone got the question?
Yes.
Yes.
So what is the maximum height possible of a tree and minimum height possible of a tree? Can you tell with n nodes?
Maximum of n minus 1.
Maximum height will be n minus 1. Okay. So in that case, all the nodes will be in a straight line, like a root has a right has a right has a left, right has a every node has only one child, or at max one child only. No one has two child. In that case, we'll have very skewed tree, something like, when draw, let me, 1, and then we have one will have a right child of 2, and then 2 will have a right child 3, something like that, and 3 will have right child 4. Okay, something like this. So this is the height of the tree. As many number of nodes will be the height of the tree, or n minus 1. It's just to depend on convention. What do you, so, root is height 0. In that case, n minus 1. If root is height 1, then it is n. Whatever we decide, we can talk about. So let's try to have a common terminology so that we don't confuse each other. So let's assume the height of root is 1 and not 0. Then what is the answer, Santosh? Nothing changes. I'm just saying if height of root is 1, in that case, it is your answer will be maximum will be n and not n. I'm just trying to avoid confusion on this. Unless whenever we talk about level of root is 0. Okay, this is something called height. There's something called level. Okay, just to whenever I talk about what is the level, we'll just think level of root is 0. 0 is root level. Okay, nothing special. Just keep in mind. Now the answer is correct. Maximum is height of tree can be n only. What is the minimum height possible of a binary tree?
Just one node.
No, there are n nodes. You have to have n.
Yeah.
Yeah. No one? So minimum height means we are trying to compress the tree completely so that we do not just unnecessarily increase the height. So what we do is we have root and we have n. We have to insert n nodes. So we'll try to have children for both the. We'll have to have both left and right node should be there. Otherwise, if we insert both the node on the one side, the height will become 3, and we don't want. What we'll try to do? Suppose they were n equal to 3. What is the better way? Either you make it 1, 2, and 3, or you make it 1. Either suppose n was 3. So this is what is the height here? This is height 3. But what if we insert into this way 1 here and then 2 here and then 3? In this case, height is only 2. So which is better way? This is a better way to decrease the height. So I'm just asking, in what is the minimum height possible? In this case, when n is equal to 3, then there are 3 nodes. The minimum height possible is 2 and maximum height possible is 3. Okay. So this is for case when n is equal to 3. Similarly, I have to tell in this when n is equal to for any n, what will the maximum height possible? Maximum height possible we know is n. Minimum height possible is, can anyone think now? No?
If we are taking every node and every node with 2 children, each of them, then how come it is a minimum?
So if we're trying to put every node has maintain that every node has 2 children, so that height does not increase. So now let's take it this case now. How many nodes this has? 1, 2, 3, 4, 5, 6, 7. So this has 7 nodes. Now this is the minimum height possible. You cannot have a size for 7 nodes. You cannot have a size less than this. Can you have something less than this? No.
No.
So and what is the maximum height possible? 7. So what I'm trying to do is I'm trying to insert as many nodes as possible at each level. But what is the maximum each level can have? This level can have only one node. This first level cannot have more than. What about this? This level can have maximum 2 nodes. This level can have maximum 4 nodes. We cannot insert anywhere. So anywhere, if next node comes, it has to go in the next level. Suppose next node comes, and that is something like, suppose
it will be 8 nodes again.
Yeah, it will be one more node. Suppose I insert one more here, something like here. Okay. So this node. So in this case, height is 5.
2 to the power n.
What? Come again?
It is continuing as 2 to the power n.
Yes. So every level has maximum 2 to the power L, where L is the level. Okay. Now let's forget about this question now. Just tell me. So what is the maximum possible nodes at each level? 2 to the power L. Is it correct?
Yes.
Yes. Nice. So I'm just saying this is one question. Also, I had one more question. What is the maximum possible node at every level? And answer is 2 to the power L. Now with this knowledge, can you tell me what is the minimum possible height? So what is height is? So the 1 plus 2 plus 4 plus 2 to the power h is equals to n. This is what it will be, and where n is the node, number of nodes, correct?
Yes.
2 to the power 0 plus 2 to the power 1. Again, we are going deep into mathematics, but I would expect people to know these kind of things. 2 to the power 3, and then dot, and the maximum height possible is, suppose h to the power h
N square
is equal to n. What is this?
N square, the sum total of whole numbers into 2.
Geometric series.
Two to the power n square.
No.
It's a geometric series. So r into r minus 1 by 2. 1 sec. 2 raised to n minus 1.
Okay. So this is a geometric progression, I understand, but not going deep into mathematics. What is the sum of just GP? If you try to find the sum of a GP, geometric progression, you will find that this h cannot be. It will be at the end. It will be log of this h, which we have height. It will be log of n to the base 2. This is what reduced to. So 0th level, first level, second level, third level, and then keep on going till h. So this summation will be equal to n. If we given this, then in this case, h is equal to log of n to the base 2. H is log of n. Height, minimum possible height is log of n. It cannot be less than that.
Yes.
Okay. Geometric progression, all you can prove using that, but this mathematical expression says us, or forget about this mathematical, I'm just saying you, if there are n nodes, then minimum possible height is log of n. If there are n nodes, then minimum possible height is log of n. If there are 7 nodes, this is 7 node, the minimum possible height is log of n. Okay. Log of n is keeping in mind like edge cases, it will be log of n plus 1. So again, I'll talk about edge cases later. I'm just simply trying to derive you the order. This is what order we do. This is log order. The height will be something in the log of number. Okay. if you talk about completely what exactly it will be log of n plus 1. Height will be maximum height of the tree will be, so maximum will be n and minimum will be log of n plus 1. So if height is, if there are 7 nodes, 1, 2, 3, 4, 5, 6, 7, the height, what is the height? Height is equal to log of 7 plus 1, which is log of 8 base 2, which is 3. Okay. Now if there are 8 nodes, then it will log of 9. Obviously, it will be a floating number. It will be a decimal. We have to take the cap. Okay, ceiling of this. This you have to think about in terms of edge case and all. Okay, ceiling of this. Okay, everyone. So height of the minimum height possible is log of n. Is that okay?
Yes.
Okay.
Yes.
Now just take this question opposite way. Given the height of a tree, h, what will be the number of nodes? Minimum number of nodes and maximum number of nodes. I am telling you, there's a tree whose height is, the height of the tree is h. What do you think? How many nodes, minimum node possible and maximum node possible? Santosh, minimum nodes possible for a tree of height h in terms of h? How many it will be? Santosh, you there?
Yes, yes.
Yeah. Yes, Suganya.
2 raised to n minus 1.
No, there is nothing called n. There is some height h. Where is n here?
Oh, yes.
Height of tree is equal to h. You have to tell me what is the max and minimum. Max and min possible nodes. Number of max and min. In terms of h, of course. अगर हाइट h है तो मिनिमम मैक्सिमम कितने नोड हो सकते हैं और मिनिमम कितने नोड हो सकते हैं h करने के लिए, हाइट h करने के लिए?
2 raised to h minus 1.
2 raised to h
minus 1.
This is maximum or minimum?
This is the minimum possible.
No, this is maximum.
One sec.
Minimum is just h. So with h nodes, we can have a tree of height h. This is a minimum nodes. इससे कम अगर nodes है तो we cannot have a tree of height h. So minimum,
yes, that is the maximum.
With minimum h nodes, we can create a tree of height h. And what is the maximum nodes? 2 to the power h minus 1. Otherwise, what will happen if we have more than this much of nodes? If we have more than this nodes, then the height of tree won't be h. It will be more than h. But so that's why these are two maximum in case. So max again, I'll repeat. So given a tree of height h, what is the maximum number of nodes we can push? We have to create a tree of height h only. So again, we have height h. So at 0th level we have maximum number of nodes, 1 node. At first level we have maximum number of only two nodes. At level 2 we have all 4 nodes. At level 3 we have all 8 nodes. So by doing this way, we can say the maximum possible is 2 to the power h minus 1. It cannot be more than that. Okay, everyone?
Yes.
Okay. You have to keep this thing in mind. Again, no one will ask you this question. This is just for you to understand trees from like internally, like how it does look like, what is the structure and all those. So we have very good tree, very very bad tree. Good in the sense that we have. I mean, the word good is bad is wrong. There are good terms. I'll talk about it later below. So like all the nodes have all children, then nodes do not have full children, only 1 children, only 2 children, that kind of things. Okay, so let's talk about this terms only. Full binary tree. A binary tree is full if every node has 0 or 2 children. Okay, so again, these terms are something not very much. You don't have to mug this up. What is a full binary tree? But these are just terminologies given to specific few trees. People will, whenever they ask you any questions regarding these kind of tree, they will tell you. Given a complete binary tree, tell me what is the type, what is the way to solve this, and then tell you what do you know what complete binary tree is. They will tell you as well. But just to keep in mind, you can keep this thing in mind your mind as well. So what is a full binary tree? A binary tree is full if every node has either 2 children or no children. That's a full binary tree. We don't have any one single children node. That is full binary tree. Okay. Good enough?
Yes.
Simple. Complete binary tree. Complete binary tree is tree if all the levels are completely filled except the last level. So suppose we have 8 nodes. So we inserted first at 0th level only 1 node, root, and first level we had 2 nodes, third level we have 4 node, and fourth level we have just node. With 8 nodes, all the nodes. I think this case will work here. This case, this is a complete binary tree. How? Because all the nodes except the last level, all the all the nodes have as many children possible. Like even if we insert a new node, we'll insert it at this position after 4. So suppose if new node comes to this 11, if we insert at this position, this is complete. But what if we insert? What if we have 6 was not there, but we still went ahead with this? So this is not a complete binary tree. Why? Because 3 doesn't have its left children. So what complete binary tree means is every node will have their both the children, and whenever they have enough number of nodes. Otherwise, only the last level can have 0 or 1 children, but that too in like order. Like left will have children first, then there will be right children. Again, the second node will have left children and the right children. That is a complete binary tree. Complete binary tree is a complete binary tree if all the levels are completely filled, except possibly the last level, and the last level has all the keys as left as possible. You see this? Last level will have is possible to have less than 2 children, but even if there are some nodes which is less than 2 children, all of them should be as left as possible. Okay, you get this? Complete binary tree. This will be a little bit useful when we read about heap. We'll have to use this complete binary nature of a tree when we read about heap. Okay. Then there's something called perfect binary tree. A perfect binary tree is a perfect in which all the internal nodes have 2 children and all the leaves are same level. Okay. Perfect binary tree is like complete, very, very triangular structure. No single children or all of them has two nodes except the leaf level. Leaf level, all of them have 0 children. Or in other ways, all the last level are the same level. They're not so full. Very, very simple circular looking. Triangular looking tree. That is a complete. That is a perfect binary tree. Okay, people. All 3 things are simple terminologies: full binary tree, complete binary tree, and perfect binary tree. Anyone? Any questions? Or shall I move ahead?
Yeah, move ahead.
Yes,
Okay.
you can move.
Yeah, nice. So now,
Praveen, a complete binary tree is a perfect binary tree.
No. A perfect binary tree is a complete binary tree, but a complete binary
yes.
Okay, a reverse is possible, but complete might not be a perfect binary tree. Okay.
Yes, got it.
Okay. Now comes balanced. Now comes balanced binary tree. So when we create our tree, we might be in a situation 2 extreme situations. One is it is very skewed, like 1 node after each. We are just appending 1 node to the right, and that is one extreme, that all the nodes are in the next level, and other extreme is we're trying to make it very complete type or the perfect type. In that case, we try to insert the nodes just as leftmost as possible, and no nodes has less than 2 children. That kind of structure we're trying. These are 2 extremes of a binary tree: very, very perfect or very skewed. Okay. Now, if we have a tree which is very skewed, will not have the benefits of creating a tree. The benefits of a tree comes only when it is closed to complete or perfect. As close it is to a perfect structure, we have our benefits of finding, deleting, and all. If it is more towards skewed structure, those benefits will not be there. Log n opposite. What is the time complexity of inserting a node? What is time complexity of inserting a node in what time complexity of inserting a node in a tree depends on the structure. But whenever we solve, whenever we discuss about tree, we assume that it's close to perfect binary tree only. We do not assume with a structure skewed structure. So that's why I'm just trying to say is we will try to keep our tree as perfect as possible. And the one way to do that is keep a balanced binary tree. Maintain a balanced binary tree. It might not be perfect, but it is close to perfect. How are we doing that? We try to maintain that whenever we insert a new node, we try to make it balanced. So there's a question. Next question I have. There's a question I have where it is. Is height balanced? This question also there. So you have to solve this question and then we'll talk about this only. So what is height balanced? I'll just tell in simple words. So height balanced tree is a tree where each node's left subtree and right subtree's height differ by maximum 1. That left subtree height and the right subtree height of every node, not just the root node, of every node differ by just 1. It cannot differ by more than 1. Either it is equal or it is differ by, or left is 1 greater than right, or right is 1 greater than left. That is a height balanced tree. Actually, this is also called AVL tree, I guess. Let me just clarify. So AVL tree, help me making the difference. Yeah, that's what the AVL trees. You might have heard this term, AVL tree. AVL tree is nothing but a height balanced tree. And what is the height balanced tree? That every node in the tree has this property that left subtree height and the right subtree height differ by maximum 1. Is that okay? Clear? What is height balanced tree?
Yes.
So that is, and why do we need this kind of trees? Because that is when we will have the benefit. Until unless they are close to perfect, until unless they are close to perfect, we will not have the benefits of the tree. We will not have the benefits of non-linear data structure. So to get the to maintain, so how can we maintain? Either we have a data only in very awesome order that while inserting it maintain the order. How can we lose the benefit? Suppose the data, suppose we are creating a BST. Okay, suppose we are creating a BST. What is a BST now? We haven't talked about BST. BST is a binary tree with the property that each node's value is less than its right subtree value, all the nodes in the right subtree, and each node value and node value is more than all the value in the left subtree. So, but BST, binary search tree, is a tree where say row node, if there's 5, then anything smaller than 5 will be on the left side, and anything bigger than 3 will be on the right side of 5. This is how a binary tree looks like. Binary search tree looks like. Correct? This is okay. This is BST. So all the benefits of BST also will be there only if they are very close to perfect structure. But what if, and how can we maintain this structure? We can maintain either our data we inserted data in a very, luckily we got data in a good order, or we tried this height balanced. While inserting only we maintain. So we'll check about insertion method in a tree or deletion in a tree. Everything we'll read about. But before we do that, I'm trying to say if we maintain the height, then we'll have the benefits. If you maintain the close to perfect structure, it will have the benefits of the tree. So again, let me just. So we have 2 questions, by the way, not just theory wise. Like, okay, we want to understand what is the BST and what is a height balanced tree, which is an AVL tree. There's one more tree called red black tree. All these special tree were developed just to ensure that the structure after inserting is close to perfect. So suppose this is a BST and the order in which came was 5, 3, 1, 4, 8, 6, and 9. If the data came in this order and we inserted it could have worked very easily. It would have been this order only. But what if the data came in this order? 1. What if the data came in or something like this? 1, 3, 4, 5, 6, 8, 9. In this case, if you create a tree, suppose the data you got in this order and you try to store, in that case, tree will be very good. But if the tree came in, sorry, I just stopped it. But if the tree came in, the data came in this order, then tree will be something like, okay, we have 1, and then 3 came, we'll insert it here, and then 4 came, we'll have to insert here, and then 5 came. So this is a very bad tree. That depends on the order in which we inserted, in which it was given. So this is a bad tree. Okay, do you get this?
Praveen, we can insert it badly and then recorrect by balancing it.
Yes, that's what. Now we have to have something called recorrect, and this recorrect cannot be very brute force. We have to have a smart recorrect. Insert and then recorrect, instead of that a very dumb one, which is like, okay, insert and then recorrect, make sure it's perfect. We have these things. We're very simple. We maintain a height balance, and by maintaining this, we can have our tree close to perfect balance. You're correct, Nikhil, that we have to, while inserting, we maintain some reordering, some restoring, some resection, so that our tree is not very bad, so that our tree is not very skewed. So what are the two ways? One is AVL, another way is red black. So now what is AVL? AVL is, by inserting, will ensure that we just cannot insert a node so that it is not a height balance anymore. So even if we get in this order 1, 3, 4, 5, 6, 7, 8, 9, we insert 1, then we insert 3. Okay, but we cannot insert 4 here. Why? Because the height of left subtree of 1 will be 2, 3, and 4, and height of left subtree will be only 0. Then nothing. Right subtree will be 3 and 4, which is 2. Height will be 2, but height of left subtree is 0. In that case, 2 minus 0 is more than 1. Hence, we cannot insert 4 here. That's why we have to do something. We have to do some special insertion that our 4 comes here and 3 comes here. Something like that we have to do. So how do we maintain that? That is another part we'll read about again. We'll read about insertion in a binary tree, insertion in a binary search tree, insertion in an AVL tree. Similarly, deletion in a binary tree, deletion in a binary search tree, and deletion in an AVL tree. Okay, all these things we'll do after some time. But suppose we have done this, we have a tree already created. We have a tree already created, keeping in mind all those logic, how to insert in a BST, how to insert an AVL tree or a height balance tree. You have to tell me, given the tree, is it height balanced or not, or is it a BST or not? These are two different questions. Okay, these are two different questions. Let's start with, is BST. Shall we start with this question first? Is BST? This is again a very standard question being asked a lot. So given this Boolean, you have to write Boolean, given the node root of the tree, you have to tell whether this tree is BST or not. So you get what is BST first of all. Anyone who does not understand what is BST? Okay, nice. Okay, you didn't get. So BST is a binary search tree. How it is different from binary tree? Binary tree is just node and then 2 nodes, maximum 2 nodes. Node and then maximum 2 nodes. That's a binary tree. But we want to maintain some ordering into the tree so that our operations are very fast. Our search and all those are fast. So we maintain a spatial ordering as well. Apart from non-linear data structure, we also maintain some ordering. So suppose this is a binary tree, B53, 53. This is a binary search tree. So how it is binary tree? Every node, what is the BST is? Every node will have the value of node will be more than all the nodes in the left subtree, and the value of node will be less than all the nodes in the subtree. So 5 is more than all the values 1, 3, 4. It is greater than all the value in the left subtree. This is left subtree 3, 1, 4, and this is right subtree 8, 6, 9. So value of 5 has to be greater than all the nodes in the left subtree, and value of 5 has to be less than all the nodes in right subtree. That is what a BST is. So let me just try to draw for you again. So this value, this is a root, and then we have a left subtree here, complete left subtree, and then we have a complete right subtree. So for this to be a binary search tree, we have to ensure that all the nodes like this, if there have been multiple nodes, will have to follow, not just a root node. Every node has to follow this. Every node's value will be bigger than all the value in the left subtree. It has to be bigger than all the nodes here, and it has to be less than all the nodes here. This is the only property we want to maintain, or less than equal to whatever. Okay, and this property has to satisfy all the nodes and not just at the roots. So this value, suppose this is root dot value will be greater than all the values here, and root dot values will be less than all the values here. Okay, now you get what is the binary search tree?
Yes.
Santosh? Okay. So given a tree, you have to tell this is a root node. You have been given access to the root node. You have to tell whether this is a BST or not.
Okay.
Nikhil, Sukanya, you got the question?
Yes, Praveen.
Have you seen this question before? Any one of you?
Yes, it is being asked everywhere almost.
Okay. So take your time. Think about it. I'll just get back in a minute. Okay. Yes. Any thoughts?
Yeah, Praveen. So what we can do is start with the root node.
Yes.
Check if the left node is less than the root node, and if the right node is greater than root node.
Can you repeat, Nikhil?
Yeah, we'll start with the root node.
Yes.
Check if the left node is less than root node, and right node is greater than root node.
Okay.
Then go one level down and do recursively the same thing.
Okay.
If it is not, then we have to reorder.
Don't reorder, just return false. Why reorder? Just return false.
Okay. Yes.
So
Yes,
tell me
yes.
tell me what code shall I write here? Can you see the screen?
Yes. One sec.
Tell me what to write here.
So we'll have a okay, yeah, root node. Then we'll check. Okay, we already have the left node and right node. One sec. So we'll create a node left equals new node.
Okay, load left is equals to
New node.
Why do you want to create? I don't understand. Why do you want to access the left node, or why do you want to create? Just do root dot left node. What do you want to create?
Oh yes, yes. Okay, yeah, this way. Okay, yes.
Okay.
And then node right is equal to root dot right.
Okay, you have your left node access to left node and right node. What do you want to do after that? Yes. Now.
If root dot left is less than root.
If left dot value is less than root dot value. Okay.
Yeah, root dot yes, and right dot value.
And right dot value is more than
less. Yeah, more than
root dot value.
you. Yes. What will you do after this?
Return true.
Return true. Else. Then false.
Return false.
Is that right?
And this if condition should run till the height of the tree. So while I don't know how to put that in code.
Let me try to help you.
Oh yeah, while root is not equal to null, I think, or something. Yeah.
So also keep in mind how the way I'm writing code. This is like so. This will show to the interviewer that you understand everything. Rather than writing long lots of lines of code, it shows okay you're trying to write code for the first time. There's no problem by the way. Okay, just give more marks if you try to write the way I'm writing. Okay, there's no special
Yes.
the root dot value is less than left dot root dot left dot value and root dot this is more and the value is less than root dot right value. If this is case, then call recursively return is BST or recursively and root dot left or recursively on the left and or recursively on the right, and then if both of them are also there, run this else return false. Is this what you are trying to do? Okay. Is this correct?
Yes, Praveen. Yeah, that true should have been a recursive call. Correct.
Santosh, Sukanya, everyone, is this correct?
Yes.
Sukanya? What?
Yes, it's correct.
There's some noise coming from your side. Right. Okay, so this is correct. This will work on this tree. Again, some noise coming from your side. Whose side is this?
From Sukanya's side.
Okay, Sukanya.
Yes.
Are you cooking something? That's
So actually I'm at home. So a bit of mood sound will be heard. That's why I'm meeting myself.
okay. Okay. So I'm trying to give a case where your code will not work. You all said it will work. I'm giving you a case where it will not work. Okay. So is this a BST? Unmute yourself if you're speaking.
No, Praveen.
No,
No, why not?
because 10 is greater than 4.
10 is very high. 10 is high.
Okay. Will your code return true or false?
So return false.
Are you sure it will return false? Try to run. Okay, wait. Sorry. This will work. Your code will work here. Let me just. Not telling. Will your code return true or false? Will your code return true or false? Is this a BST first of all? Is this a BST?
Oh yes, now it will return true.
Is this a BST?
No, this is not a BST.
And your code will return true or false?
True.
So can you now correct your solution?
Praveen has a lot of background noise. I think Sukanya, can you just check? I can't hear you.
Yeah, now let's go ahead. Sukanya has muted herself. So, Nikhil or Santosh, you see that your code is not going to work for this case. This is not a BST, but your code will return yes, it's a BST. So how can you change this? How can you improve this? How can you make it work? Thinking, you people are thinking?
Yes, Praveen.
Okay.
Present, they also have another criteria, that there cannot be duplicate node.
That is not a problem. You can or cannot have repeated nodes. You can take care in your definition of BST. The definition is if a root node. So the definition of BST is all the nodes in the left child should be less than root node value, and all the nodes should be greater than or equal to. You can just keep that equal to in mind. Right child or right you can have values greater than equal to, and that you can take in the definition. Okay. Okay, so try to think. I'll also discuss is height balanced, and then we'll end the class. I would like you people to think about this question very. Take care of this question, like think and keep on discussing on the WhatsApp so that I can give you. Also, we'll discuss in next class. But I would like you to think on both: is height balance and is BST, both of them. So let's discuss is height balance as well. These two are very interesting and good question. These two are being asked a lot in interviews. I as much as I have seen interviews, these two questions get asked a lot. Type of question also gets asked a lot. So we'll discuss both of them. Try not to read from anywhere, like copy from anywhere. Try to think yourself, okay, and then keep on discussing on the WhatsApp, so that I can think about and try to think as much as possible and write everything on the WhatsApp. This is what you're thinking, so that I can suggest you where you're thinking now. Okay, this will take time. Otherwise, this is a 45-minute interview question. This is BST. Someone to give when I give this question, someone to write the working code. I give them 45 minutes overall. So let's now discuss is balanced. So okay, I'm discussing is balanced now. Given a tree, you have to tell is height balanced, not balanced. Is height balanced? given the root node of a tree, you have to tell whether it is height balanced or not. And what is height balanced? Height balanced is height of the left subtree of every node and right subtree should not differ by more than 1. Everyone know what is height balanced tree now?
Yes.
Yeah. So can someone try to? Yes.
So Praveen, you will do while root bracket.
Okay.
Then instead of doing root dot value, we will do root dot next.
What is root dot next? Don't say a random thing.
Uh,
Tell me what's right. If
root.
Okay, so before we solve this, let's just solve another question. Find height of a node in a tree. What is the height of the node of any node given? Okay, what is the height of the root node? Can someone find the height of the node? Can someone implement this first? Find the height of the root. Find the height of the tree, where root node is given. What is the height of the tree? How will you write the code?
We can traverse the tree and keep a counter on the number of nodes visited.
Okay, and then?
And then use the formula.
No, but that formula is not exact number of nodes. That is the maximum minimum value. The ranges, they're not single value.
Okay.
That formula is applicable only for a perfect binary tree. Okay?
Okay, yes, correct. Yes.
So not before this, given a tree, count the number of nodes. Forget about now. I'm doing very simple question only. Count number of nodes in a tree where root is the node. Can you tell me what is the number of nodes in a tree? Okay, how will you count? How many nodes are there in the tree? How will you find? Yes, come again, Sonia.
We found the present sound of text now, right?
Okay, there is noise and there is disturbance and then your voice is too low. Can you?
There is a level sound that we found that level. Then we finally
No. As I said, if you're trying to use the formula now, those formulas are not for exact numbers. Okay, so you have to think about a generic tree, which is not a perfect or a skewed or anything. These are just an average tree. They're not a special case tree. All of them are perfectly balanced or no, all are skewed, completely skewed. Okay, for the random tree, how will you find the number of? So, given the access to the root node, how will you find number of nodes? Can you tell me? So think nothing. कि तुम यहाँ पे हो, yes.
Pramesh, we can while root is not equal to null.
Yes.
Root is equal to root dot next.
Root. Again, what is root dot next? Don't say random things, Nikhil. What is root dot next?
Meaning I'm increasing the I don't root. And I mean next pointer.
No.
Okay,
there's something called left. There's something called left, and there's something called right. There's nothing called next.
Oh, sorry. Yes. Root is equal to root dot right, and root is equal to root dot left.
So why do you want to do both things? Root equal to root dot left, and you also want to do root dot equal to.
No.
Praveen, I think we need to call it in a recursive way, in right and the left separately.
Go ahead. You're on the right part. Tell me what you write. So you have to do recursion. That's the hint. Recursion is needed. Now what?
While root node is not equal to null.
Okay. We'll not write that code. I'm just trying to write the recursion. So forget about total number of nodes. Just tell me, can we use this method recursively? Root dot for right node, and also can we call this similarly for root dot number of nodes in right subtree equal to this. Since this is a recursion, we know this will work in the left subtree. Now suppose we have calculated this recursively. What will you do? Suppose
so
you call it. Yes.
So now we got the right and left root.
Yes.
Height of the right side and left side.
Not height. Number of nodes, not height. This is number of nodes. Yes. So we know the right subchild has 10 nodes and left subchild has 12 nodes. So how many total nodes?
22. Okay, number of nodes on right plus number of nodes on left.
Yes, simple. I don't know why you're taking so much time to think this thing. So if you know left has 10 and right has 12, total will be 12 plus 10 plus 1. 1 itself. Correct? Is this correct?
Why do we need one, Praveen?
अरे लेफ्ट में 10 है, राइट में 12 है, मैं खुद भी 1 हूँ, टोटल मिला के 10 प्लस 12 प्लस 1 होगा ना. If left has 10, right has 12, then total number of nodes will be 10 plus 12 plus itself 12. So this 3, left has 3, right has 3 nodes.
Got it.
Okay. Mute yourself if you're not speaking because there's lots of disturbance on your side. Okay. Yeah. So we have, by doing this, we know we have implemented our count number of nodes. Okay, now just a minute. So just handle some edge cases. If root is there, then do this. Return 0 if root equal to null. If there is no nodes, this is the terminating condition of a recursion. So every time we write a recursion, we should always have a base or terminating condition. Otherwise, this will never end. So yeah, let's keep going. We are doing this. We can return 1 plus this, correct? And now I will try to write some optimize the number of lines of code which is not needed, just to make it look small. Correct? Is this?
Yes.
Everyone? Nice. Now
Yes.
using this awesome line of code, you have to write the code in chat very fast to find the height of the tree. Or before you do, what is time complexity of this? Can someone tell me what is time complexity of this? Before you find the height, who can tell me the time complexity of finding the count of the nodes, finding the total number of nodes in subtree? What is the time complexity? Anyone?
Order of n.
N plus n. Yeah, order of n.
And how did you come derive that?
Yeah, so you're going on the left side. You're going towards each node. So you are doing n nodes on left side, n nodes on right side, plus the your root node. So n plus your root node. So that is the that's how I did it.
Actually, a good way to say is we are just going to a node. Okay, this is going to a node and then doing few very small thing and then just visiting each node only once. We go to root and then we call recursively on left child and right subchild, and then we go deeper. We don't have to do something repeating on each node. Every node we visit and we just return something. Okay, we don't do anything repeating on each node. So we visit all the node only once, and so hence the time complexity would be order of n, where n is the number of nodes in a tree. Okay, correct. Now
Yes.
tell me this code. People write code in chat fast. You have to write a code for this very fast. in the chat, and you can use the same logic or whatever which we have done here.
Praveen, now I think we need to calculate this right side nodes and left side nodes in separately, and if the right side is greater than of left side, then you have to return the right side node with the height of that string.
Yeah, so you are again on the correct path. Just try to write some code in a chat, and then we'll discuss.
Okay.
Okay, so if count of this. Okay, so let me copy and paste what Santosh had written. Okay, so if so he has first, everyone can see this. I'm trying to verify Santosh code. Okay, so he has first calculated the height of the right subtree and right equal to find height. Yes, Sukanya, you say something?
No, it's okay.
Mute. Yeah, so right equal to find height of right subtree, root dot right, left equal to find height of left subtree. We have both things calculated. Now, if right is more, then return right. If left is more, return left. It's not simple. It's just you have to add one more, one plus right sub, and that's it.
Okay.
Is this correct, everyone?
But why are we returning the height?
Because I have asked to calculate the height.
We have to do height balance.
We have not yet reached there. I'm just trying to implement find height. Will height balance will do first. Before that, I wanted you to implement count, which you have done. Then we want to implement find height. I'm doing this. Height balance will come.
Praveen, why are we returning 1 plus, right?
You tell me
Is
why.
it because is it because we are at the root node, meaning we are at the start, we are at that start, and so we are returning that plus the right.
No. Yes, that is there, but just think, I am at the root node or I'm at some node. So what is the height of tree? So whatever is the height of children plus 1, so height of children tree plus 1. Now that's what logic says.
Yes.
That is
Same
1
thing.
plus.
Yes.
Yeah. So he has first found the height of the root right subtree, left subtree, and whichever is more will matter. Whichever less won't matter in calculation of the height. Suppose we have a tree like this, 5, and then we have 10. So here if you see, when we are calculating the height of this tree, we're starting from 5, and height of 5 will depend either on height of 10 or 3. Now it depends on 10 only, not 3, because 3 height is just 1, or 10 height is 1, 2, and 3. So height of 5 will be 3 plus 1 and not 1 plus 1. Okay, that's what he has done here. Height of root we are calculating, and we have first calculated height of the right subtree, height of the left subtree. Once we have both the heights, we check whichever is more, we'll return that plus 1. Is that okay?
Yes.
Nice. So now we have the height of the tree as well. Just let me write another code for you. The base condition which we will try to maintain. When you do it, you have to try to write that as well. I can skip, but you can't. If return 1, if or 0, if equal to null. Okay? Correct? Now comes our height balanced. Who can tell? So take this again. This is also similar to our verb to implementation, like recursion is there. Similar kind of recursion. In first recursion, it was very simple. No if else, nothing. Just simply add and return. There was some if else and then return. And this will have even more if else and return. But this is all similar kind of implementation. So you should be able to do this as well. But I'm sure you will not. You will be returning. And the problem will be time complexity. But that is okay. You try to implement just by the brute force. Just implement this is height balanced. And then we'll talk about it in the next class. When we'll have the next class? Sometime before Saturday. I'll confirm later. Sometime before Saturday. Okay?
Okay.
Okay. So you have just 2 assignments, is BST and is height balanced. I'm copying this, all the content which we just discussed into the document for your reference. And then you have your 2 assignments. And plus one more assignment was reversal linked list in group of K. Okay, there's 3 assignments, not 2. Try to do as many as possible. And then we'll talk about tree traversals. Tree traversals is something we'll talk about in the next class. Let me paste everything here. Yes. Okay, I'll correct this later. Anything you want to ask? Or shall I end the class?
Praveen, I have one doubt. It's not related to trees, so it's just a small doubt.
Yes.
So yeah, 5 minutes. I'll take.
Yes, tell me, go ahead. If anyone want
Yeah,
to leave?
I just sent you the code on by email. So I just wondered.
Hmm. Doubt in deletion. Deletion in linked list?
Yes, Praveen.
Okay. Linked list deletion. Yes. Tell me, what is the doubt?
So I'm trying to delete a node. So any node. So I'm specifying the date. I'm giving that whatever, like say I'm creating the linked list say with value 1, 2, 3, 4, 5, and my head I'm inserting at the head. So the head is currently pointing at say at the last number that I've inserted.
Yes. Okay.
So now I'm deleting any random value. So I'm just calling delete node say 5. So
Okay.
so this is my code, but I think it is wrong. So I'm not sure, like I'm getting some
Okay.
error when.
Yes. So you want to delete 5, and this is the code you have written, and you want to find the error in this. So others
Yeah.
also think, I'm also thinking, others try to find the mistake in this code. So you have delete node int 5, then previous count equal to head, int count equal to 0. Why are you maintaining count, Nikhil?
So count will go from the head from the previous where the head is till my data node. So when I want to delete say I want to delete 5. So
Are you
I
saying
need to
are you saying that your all the nodes are in this order? Like first node is 0, second node is 2, third node is 3, and then
no
fourth node
no
is 4. Then
no no
there's
no
no sense, then there's no sense of maintaining count. Like this count is what less than data. Data is what 5. So first you will match 0 and 5, 1 and 5, 2 and 5, 3 and 5, and the moment you reach fifth node, so this is like in deleting at fifth index. What you try by doing this count, maintaining count, by maintaining a count, how many nodes you have seen till now, and maintaining that count and comparing that data is like deleting, not deleting 5, but it's like deleting fifth index element. That is what it feel like. This implementation looks like you're not deleting node whose data is 5, whose value is data, but you're deleting fifth node in it. That is how this implementation looks like. Do you get the problem? First problem. The first problem is
yes
this implementation is not delete the node whose value is data, whose value is 5, but this implementation looks like delete the fifth node in the linked list. That is what it looks like. So that's first error. Try to solve that error. Try to solve that error first, and then we'll talk about this also. Send me
yes
again. Okay.
yes okay, Praveen. Yeah, thanks.
Okay. Okay then. I'll stop here.
Okay.
Thank you.
Yeah.
Thank you.
Thank you.
Yeah, thank you.